Hello, we are Team Vyadh. We are a rover team from Vellore Institute of Technology, Vellore. We represent to you the latest edition of our rover, Dream 2.2.
We were founded in 2015. Now we are a group of over 40 students working passionately towards building a legacy of excellence. From ranking amongst the top 20 teams globally at the International Rover Challenge to breaking into the top 10 at the International Rover Design Challenge and ranking second in Asia at the European Rover Challenge, our journey is a testament to the power of learning from every competition. With this incredible momentum, we continue to push boundaries and innovate at every turn of our journey.
We have a dedicated workspace for Team Vyadh where over 50 students from various domains build and design the rover. Initial design concepts formulated through collaborative brainstorming sessions are translated into detailed engineering blueprints. Software engineers develop the rover's control systems while mechanical engineers oversee its physical assembly. The electrical engineers work on the power distribution while the main focus for science remains to search for extinct and extant life. The workshop becomes a hub of activities with 3D printers operating and metal components being integrated. Ultimately, the workshop transforms into a testing and upgradation facility where the meticulously crafted rover navigates a simulated Martian terrain, serving as a tangible demonstration of Team Vyadh's commitment.
A rover boasts a chassis constructed entirely from aluminium T-slots, fortified with a hardwood foundation for enhanced structural integrity with the incorporation of an economical budget and a lightweight structure. But what truly sets a rover apart is its suspension system, employing an altered double rocker design, ensuring unparalleled durability and smoother rides across rough landscapes. The modified differential equipped with a two-tie-rod system guarantees exceptional stability in all scenarios. Our wheel assembly combines aluminium and 3D printed components, minimizing vibration and energy consumption, ensuring optimal performance and efficiency. Extensive CAD and CAE tools were employed to scrutinize motion dynamics, simulating conditions akin to those on Mars. After rigorous testing, we have manufactured and assembled every component, ensuring the rover's readiness for its motion. With 5 degrees of freedom, our robotic arm maneuvers with precision and effectiveness encompassed with sophisticated actuators, servo motors, thrust bearing, and an IG45 geared motor, delivering increased torque and power. The integration of rotary encoders and adaptable SmartLex motor drivers further elevates the efficiency and reliability of our robotic arm, rendering it a robust solution for a myriad of tasks necessitating intricate manipulations.
Our transversal system comprises of 4 industrially-grade IG52 motors having 210 RPM and built-in encoders. These motors are controlled using MD30C motor drivers. We are using customly designed PCBs for various subsystems of our rover, such as locomotion, power distribution, and robotica. Our onboard power supply consists of 2 LiPo batteries of 22.2 volts and 16,000 mAh. We use DC to DC buck converters to step down the voltage for the usage of the onboard computer and communication setup.
Our robotica has 5 degrees of freedom.
And we are using TV6600 motor driver to control a stepper and the gripper, and 4 MD10C motor drivers to control the links and the joints of robotica. We have an operational kill switch on the rover for emergency stop, which can be seen mounted on the rover.
Our 2.4 GHz communication setup enables us to have seamless and uninterrupted communication between the ground control station and the rover. The setup consists of a Rocket M2, Nano Station Loco M2, and an omnidirectional Ubiquiti antenna. The Rocket M2 connected to the omnidirectional antenna present on the rover connects to the Nano Station Loco M2 at the ground station. IP cameras are accessed from the rover using their own unique IP addresses for live camera feed. This ensures low latency and control over video enhancement. Our GCS, or ground control system, is a Flask-based website with a React frontend that we use for the purpose of displaying various sensor data for science-based tasks.
The SSH protocol is used for remote access to the onboard computer's terminal to run the custom algorithms required for autonomous navigation. Using data from a depth camera, we generate a 3D map of the environment. This map is then utilized to create a 2D grid map where obstacles are identified. This grid map serves as an input for the Nav2 stack. The RealSense depth camera is employed for object avoidance and Aruco DAG detection. The algorithm leverages OpenCV libraries to detect the ID of individual markers, as well as to estimate their pose and distance from the camera. These estimations are crucial for enabling autonomous navigation. This data, along with additional sensor input from IMU and GPS, is transmitted via ROS2 topics to the Nav2 package. The Nav2 package utilizes the combined input to generate a path for the rover, enabling autonomous navigation.
Our science team has chosen the hypothesis to search for microbial activity in the Lily region of Mars. Geomorphology of the site is studied using a digital microscope which has been mounted on the rover to visualize the texture and size of the soil particles. Soil samples are collected from this sampling site using an auger and is transferred to the sealed sample containers and will be delivered to the laboratory for further testing. Samples traced earlier will be collected from the ground using the robotic arm. Hypothesis is investigated by employing two biochemical analysis of samples in the laboratory and onboard sensor analysis. Catalyst test and biorate test will be performed for investigating the hypothesis. Catalyst test is performed to determine the presence of catalyst enzyme in the collected soil sample by using hydrogen peroxide. Biorate test is performed to determine the presence of proteins or peptides in the soil sample. These tests are major indication of microbes as well as organic matter that can possibly support life. The environment and soil condition monitoring on the rover are executed by a sensor array which offers continuous monitoring. Temperature and humidity of the environment is detected using the DHT2 sensor. Soil moisture sensor measures the water content present in the soil. MQ4 gas sensor for detecting the content of methane present in the environment, and BMP280 sensor is used to detect atmospheric pressure and the altitude at the site.